Okay, I hope my voice is clear and everything will work perfectly. I'm sorry I could not be there in person, and thanks a lot, first of all, for the organizers to giving me opportunity to talk in this interesting workshop here. So today I'm going to talk about the modern challenges in the gravitational wave parameter estimation, where in fact, gravitational wave parameter estimation itself is a modern field because gravitational waves that we are started to come, and we have to tackle them soon or in the near future, especially when the detector sensitivities are getting better and better, and we are getting events in the parameter space where sometimes maybe there are some systematics or something else. And so this is a brief outline of my talk. I am going to briefly review the parameter estimation technique that we use today currently, and then I'm going to talk about the systematic errors, and we'll try to quantify different type of systematics that can come in the parameter estimation and why we need to worry about them right now, and also when to worry about them if we are doing parameter estimation. And then I will focus on two specific type of systematic errors. A, that might come from the non-stationary noise. The model may or may not be perfect. And also moving forward, what are the new challenges in the horizon, and we'll see if we can initiate some discussions on that. So first, let's have a bird's eye view of the gravitational wave data analysis in general and parameter estimation in specific. So signal from binary described by a set of parameters, for example, its masses, its spins, distance, inclination, and its location, coalescence phase and polarization angle, etc., etc. And in general, the gravity can be categorized broadly into two categories. One is the searches, and other is parameter estimation. So in searches, our focus is on to identify if there is a potential gravitational wave candidate. We call it triggers, and then we use a template bank made up of either one or multiple waveform model, and we use the techniques of match filtering to basically get something called signal to noise ratio, and then we do some more end product of the search pipeline is some sort of ranking of the triggers that we have in multiple detectors. These triggers are ranked according to whatever ranking statistics we choose, and the top few triggers that we are confident about that they are, of course, gravitational wave triggers. We sell it to the parameter estimation pipeline, where we study them in detail and try to extract all the source properties like their masses, spins, or whatever. It's a mandatory slide for any parameter estimation talk is the base theorem. So what we have is, for any situation, is that we have a model in context of gravitational wave. We assume that the data stream or the time series data consists of noise, which we model to be Gaussian and stationary, and then occasionally there will be some transient signal and also sometimes some glitches. So this is, let's say, roughly our model. And using this model, we construct a likelihood function with some parameters of the model. Then we have this prior probability distribution, and using them our end goal is to construct the posterior probability distribution from the model and the data that we have. Now, in this whole process, we have statistical error, and there might be systematic errors if either our model is not correct or we are doing something wrong in the data analysis. So statistical errors basically are related to the width of the posterior probability distribution. For example, here, if we assume a parameter theta or 1D marginalized parameter, the posterior distribution, then the width of this posterior distribution is related to its statistical errors. And it basically depends on the signal loudness or the detector sensitivity. So better the detectors, you have narrower sigma of this theta. And then the systematic errors are difference between the true value, whatever it is, and the recovered value. And the general origin of this might be either mismodeling or the data analysis artifacts. Now, when does the systematic errors become important? It's when the ratio of the systematic errors, this bias to the statistical error is of the order of unity for any of the parameters that we are looking for. And this is the regime when we need to now think about how can we mitigate these systematic errors if there are any. So now let's go towards the classification and the sources of the systematic errors that can arise in this whole process. One is, for example, it can be broadly categorized into three categories. One is data analysis artifacts. For example, our assumptions that our noise is Gaussian and stationary may not be true sometimes. And in fact, it has been studied that roughly 3 to 5% of the LIGO-Virgo data is not Gaussian and stationary, so it is a non-stationary data. And then there could be glitches near the signal itself, which could affect the parameter estimation, or even if we know how to remove the glitch. For example, there are reconstruction method in which we try to do the de-glitching of the frame files, in which the data characterization team, they basically reconstruct the glitch and the signal and try to remove the glitch from the frame, and then they call these frames the cleaned frame. These glitch mitigation schemes can also introduce some sort of systematics. So this is another systematic error. And then when we go to the third generation detectors, maybe, or even soon, we might have to deal with the overlapping signal. And also, we assume that we know detector calibration quite well. And right now, detector calibration is not at the uncertainty in the detector calibration is not at the level that could cause problems in the inference of loud signal, but we will reach there sometime soon. Then the other categories could be missing physical effect, which means that our waveform model may not be complete. It could be an eccentric system, but we do not have a fully processing an eccentric waveform model, which also include higher modes, even though there are people who are working towards that. Or there could be processes, physical processes that we have not accounted for. For example, it could be microlensed, or there could be some environmental effects like line of sight acceleration, or it's in some weird dark matter potential, etc., etc. Any physical process that we can think of that we have not accounted for in our study may cause the systematics through these missing physical effect category, if those effects are there. And then the waveform modeling uncertainties, inaccuracies in the waveform modeling scheme itself. So our waveform models are calibrated to numerical relativity simulations. So it may happen that when we are fitting these analytical model to the numerical relativity simulations, there are some errors introduced there. It could be because of the numerical relativity simulations are sparse in some region of parameter space, and we are just extrapolating in between the NR grid or a simulation grid. Or it could be that the NR simulations themselves may have some inaccuracies. For example, in the case of binary neutron stars, we may not include all the matter, or there are some thermal systematics or anything that we can think of that are not included in the numerical relativity templates. So This is an overview of what can cause the systematics. So I will pause at this stage if there is a quick question before moving forward. Then let's go to them maybe one by one, and we will not go through all of them, but maybe let's try to focus on few of them. So currently we deal with the two types of data analysis artifacts. Frequently, one is the non-stationary or non-Gaussian noise, and a fraction of detector times are affected by this. But there are also, and also the glitch near the signal. So there are many events, 191109, 231123, and there are many other systems near which there were some glitches, and then data characterization team produces some cleaned version of the frame file by removing those glitches, and also this is another data analysis artifacts. But in the 3G era, where the third generation detectors like Einstein telescope and Cosmic Explorer, or even the Voyager, we might go into a regime where there will be overlapping signal or the confusion noise from the unresolved background. And in that era, the correct estimation of the power spectral density of the detector itself might be a problem. And then there could be other issues like the data gaps and the PSD changing through the very long signal of, let's say, tens of thousands of seconds long VNS signals. And during this time, the detectors noise may not remain same, and we need to account for all those type of things. So I would now focus on the non-stationary noise. So we looked into this issue of non-stationary noise in current generation detector and also in the future generation detectors, and Mazon et al. By studying the one of the O1 chunk, they have identified that roughly 3% of the data in that chunk was non-stationary, and then it may happen that some of the signal may lie in that chunk. So what will happen if we do not account for that non-stationary behavior of the noise? We may misestimate the power spectral density, and which may cause the misestimation of the width of the posterior. Okay, at the first glance, it may not look like a serious problem, but what can happen is that it can affect some serious science cases like demerger localization. If we see my cursor, okay, if not, then I would just say that the first plot, it shows an example of a Gaussian stationary noise in which so we have 4 blocks, and the top left panel, this is the noise time series for the Gaussian and stationary noise, and we calculate in the upper panel something called the PSD variation statistic. So what PSD variation statistics is, it's a filter which gives you a rough estimate of ratio of the long duration PSD to the short duration PSD. So if the PSD is not changing or not drifting, then it should have a Gaussian peak around the 1. This is how the PSD variation statistics is constructed. Now, in the all other panels, we have introduced the non-stationarity in the time series data that you can see in the lower panel, and then the PSD variation statistics can track those non-stationarity. Now, signal, if there is a long signal which suffers a duration of non-stationarity during, let's say, some of its signal length, then what can happen is that we can identify the frequencies during which these non-stationarity was there, and then we can construct something called an effective power spectral density along the track of the signal, and then use that power spectral density to calculate, to either calculate SNR or do parameter estimation, and this gives you the unbiased SNR and also the unbiased localization errors. So this is one of the early approaches to deal with the non-stationary noise for the long duration signal, but it also needs some improvement. For example, the way we treat the PSD variation statistics or estimate the PSD variation statistics is we do not account for the frequency dependent changes at each time. So it may happen that the whole noise floor is basically going up or down, but this could also be the case that the noise floor is not going up or down, but maybe there is a frequency dependent change as a function of time, and those are much more complicated scenarios, and these are the things that people need to study, and also perhaps the machine learning and AI tools can help us, because these things are very computationally expensive. So we need to design these algorithms which are fast so that it can help in the scenarios which are most important, for example, the pre-merger localization alerts, etc., but also it can be feasible to do parameter estimation. Now I will switch to the waveform modeling uncertainty. So there is an uncertainty in the noise characterization or the systematics in the noise characterization. Other are the waveform modeling uncertainties itself. So there is no need to convince you all that we already are in a regime where the waveform systematic is a serious issue. So for example, this is the IMR phenome model and effective one-body waveform model in case of the 150914, and on the right-hand side, various waveform model for the masses for 231123 signal, and on the right-hand side, it's all over the place. And we know that we have to account for systematics now, or we have to design our pipeline in such a way that the waveform systematics has to be accounted for. So it's a quick overview of what are the current approaches of the waveform systematic. So first, what are waveform systematic? It is when the description of the waveform itself may have some errors. How much? Okay, we don't know yet, but let's say the easiest way to check is that you take different waveform models in a given region of the parameter space and see how close they are by calculating their mismatches or overlap, and whether doing PE with different waveform models give you consistent result or inconsistent result when you have all other data analysis artifacts under control. So there are multiple approaches. So I will just quickly give you a very quick overview. One is, for example, the probabilistic models, in which the waveform are not just one curve, but a family of curves, and which comes with the, let's say, appropriate weights. And you provide it whenever you're calling a waveform model, a distribution of the curves are coming. And then you can use that information in your parameter estimation pipeline. The other approaches are the mixture model. So you take multiple waveform model while calling the likelihood function, and you assign appropriate weights to each waveform model, maybe based on how close they are to the numerical relativity simulation. What is the mismatch of the, let's say, one waveform model with the closest NR simulation available in that region, and then assign more weight to the waveform model which are let's say which are closer to the NR simulation. Or you can do it posteriorly, where once you run with a different waveform model, then you mix the posterior sample by providing appropriate weight, or maybe agnostic, just 50-50. Then there are Gaussian processes regression approaches, where people use a little more complicated corrections in the waveform model using the Gaussian processes on the fly while they are doing parameter estimation. And then last but not least is this marginalizable over the NR calibration parameter. So the NR simulations also have their own resolution errors, and also there are errors in the while calibrating to the NR simulations. So there are approaches to allow different types of errors. Now it's good time to just think what are done in the calibration uncertainties correction. So we know that detectors, when the strain is provided, the amplitude and the phase corresponding to those strains are not perfectly calibrated. There are some uncertainties associated with them. So how they are accounted is basically the detector characterization team, they do lots of hardware injections, and then they use their calibration model and provide the amplitude and phase envelope as a function of frequency, as shown here for around 150914 signal. And then these corrections are applied on the strain while doing PE. Now, can we use the similar approach in the waveform systematics as well? So for example, if the waveform developers provide us these similar uncertainty envelopes, and which we can use in the strain correction, the only difference would be that the calibration corrections are applied when we project the strain in each detector, but the waveform uncertainties should be applied in the source frame or the signal frame before projecting them into the detector. So this was the idea that we came up with, and we tested. Like, let's say we parameterize the strain of the waveform model itself in the source frame before projecting it into the detector, and then we parameterize our ignorance about how much errors in the phase and amplitude of this waveform are, and then just like the calibration envelope are applied, corrections are applied, we apply the similar corrections but for the waveform. So here are some simulations done for this scenario. So what we did was we introduced our own errors on a known waveform model and injected them, and then we try to recover with the model which do not know that there are errors, or assuming that those model are, there is no error in the waveform model, and then B, by applying those corrections or the uncertainty envelopes. So the thing that you should be looking for is the orange curve. So whenever we do not allow, so whenever we introduce the errors in the model, then there are biases in the chirp mass recovery, and the last, the bottom plots for each of these curve is when we apply the relative phase corrections or the correct correction in the model. Not only that, we can also recover the frequency dependent errors in the phases. For example, this is an injection at 500 megaparsec with SNR of 65 in the advanced LIGO detector sensitivity, but this is more visible when you go to the 3G type detector. This is at 100 megaparsec with the same advanced LIGO sensitivity, and this red curve is the uncertainty that we introduce in the injections, and these you can see that it's recovered at different nodal points. So this is this approach in principle works. Here we also quantify that there can be two types of error in the waveforms. So we quantify them as a type A errors and type B errors. So type A errors are the type of errors where the waveform model cannot reproduce the true morphology of a signal. So for example, you can go over all parameter space, but somehow there are some residual left. The true signal can never be reproduced. And the type B errors are what? Those errors in which, let's say, the waveform can reproduce some that particular morphology, but for different set of parameters. So which means that the bias will be introduced because of that. So for example, let's say we are using a processing system or eccentric system. It may happen that some combination of the processing and some other parameters can mimic maybe some region of the eccentricity or vice versa. It's just an example, it's not the true example. So which type of errors are easier or difficult to mitigate, and what are the schemes that we need to use? I'm not going into that. I just want to just flash this out that we also need to think about these things. The second last is basically the missing physical effect. Another systematic that can come into our analysis is when our waveform model do not include those physical effects that we do not thought about. So here is a very toy example. So for example, here we are showing 10 injections and recovery for the chirp mass for different scenarios. And the violet scenario are when we do the precessing injection and precessing recovery. And the top right one is when we do precessing injection but non-spinning recovery and we expect biases. But when we apply our framework, which is the bottom left, as you can see that the biases are reduced, which is quantified by the delta m, the bias divided by the sigma of m. And also on the right hand side, we are applying our framework but in the wrong parameterization. So this is just to show that this can also be agnostic to the missing physical effects. And we also have to apply it on the real events. So allowing for those delta A's and delta phi's basically account for these systematics in this particular framework and for this particular event. Not just that, on the left side we are showing the chirp mass posterior for raw frame files in which no deglitching is done, and with the deglitched frame files. So you can see that if you are doing your PE runs on raw frame files or the deglitched frame files, you might get different results. But on the right side, we apply our framework, so it doesn't matter whether it's a raw frame file or the deglitched frame file, the posteriors are consistent and the multimodality is gone. So this is also one good thing about this framework. And also it picks up the delta phi variation from deviation from zero, where the around 35 between 35 and 40 solar mass, 35 and 40 hertz frequency, where the glitch, the scatter light glitch was there, and you can see that because it's a relative phase, so after that frequency, this is just builds up this error. So this was just a flash of some results that we got in this framework. The summary is that the systematics are important. I'm not going to go through all of them, but I will mention that we have a framework in which we can account for different types of systematics, waveform systematic as well as the data analysis artifacts. But there are some challenges, and for that we need more research into it. So for example, the computation cost increases. We need 2 times the number of nodal points additional parameters, so 20 additional parameters. Even though when we apply the calibration, we are anyway using 20 additional parameters per detector. So switching on 20 parameters more is equivalent to having 1 more detector in terms of number of parameters only. And of course, for each system, we need to figure out what are the optimal number of nodal points. For example, for BNS system, we might need more number of nodal points, and that would be more computationally expensive. And we also need to disentangle the waveform systematics, calibration systematics, and the data analysis artifacts, because we are already in the regime where we need to know which thing is causing these systematics. And we are going towards a comprehensive data analysis pipeline, which is required even today, not even for the 3rd generation detectors, but it will be essential in those times. So with this, I will stop here, and thank you for your attention.
So start with a quick question. I hope I'm audible, Smith. Can machine learning be used to better understand the detector calibration errors, which can be disentangled from other kinds of errors by looking at frames where there is no signal? There we expect the same calibration errors if the frame is near the frame of interest, and we can come back and disentangle it by looking at the frame with the signal, which may have waveform systematic errors and so on.
Yes, in the future, but at least with the calibration. The good thing is that so for example, right now the phase errors in calibration are 0.02 radians, and amplitude error are just 2%. We found that they are not enough to cause the observable systematics, but it will change in the future for Voyager, or let's say if we have a uncertainties of 10% or 15% in the calibration, yes. In that era, then yes, you're right, maybe we need to apply some sort of machine learning techniques in the detector, because detector calibration is an ongoing process.
Right.
And we need to...
That's what I meant, because
sorry?
Even at low latency, we don't have these kind of errors. Even at low latency,
exactly.
Our calibration errors are 10 times or 100 times this. So
exactly. So basically, yes, we need to be ready for this, and we need to prepare this thing. And plus also, there is another issue with the way we apply calibration in the detector. There was a calibration correction. We use 10 nodal points and these cubic splines, but when we go towards the lower and lower frequency, so when the detectors are getting better at lower frequency, maybe 10 nodal points might not be enough, and then the same problem that we might face in the waveform systematics, the calibration also, we might need to come up with some different approach to basically correct for the calibration, some Gaussian processes, and maybe train them with the machine learning or some network on the fly, and something like this has to be done sooner than later. Yeah.
Thanks. Okay.
Hi, so what's the functional form of these additional parameters that you choose, delta and delta phi?
There is no functional form. These are the data driven. These are model agnostic. You have to just provide a Gaussian prior or maybe uniform prior around these values. So for example, this recovery that you are seeing, we just provided the Gaussian prior by DDoF, which would just take them. And then because the signal loudness itself recover the this particular whatever functional form we injected in, which was random.
Hi Sumit, can you hear me? So,
yes.
So in this particular plot, so can you understand that why this 500 Hz is too much? It's too wide for. Is it due to the duration of the signal or?
No, because at the signal, if you calculate the merger frequency, it's somewhere between 200 and 300. Basically, there is no part of the signal there. Yeah. We just use the nodal point such that because there are some points in the prior which were merging at the below 500, not beyond 500. So we need to account for that point. But this basically is giving us prior. So last point is not there is no SNR in the signal. Oh, yeah. So that's the reason that it's wide. Yeah.
Okay. Thank you so much for that very interesting talk. So the next.
Thanks everyone.